All right. Let's begin our lecture. This is the last lecture of the semester, and so we've got normal physics stuff to talk about, and we've got exam preparations to talk about. So let's get to it. First of all, SSG signups, second round. We now have information for all of them in the schedule page, and so you can go in there into the schedule page and look it over. The first group, the V for Victory group, is going to have first shot at signing up, and that's like last time. It was called Group 2. This time it's Group V for Victory. You'll go in at 4 o'clock, and you'll have 2 hours to, go in and sign up. And you can go to the page that I have set up for you and look at the schedule right now. But sign-ups will begin 4 o'clock on Friday. And then at 6 o'clock, everybody else will be able to, rumble in there like last time with the Buffalo Stampede. So if you get, by the way, I have a public service announcement or a question by way of public service. Did anybody that signed up at 7 p.m. or later do it by iPhone or Android phone? 1, 2. Okay, so what did you use, the iPhone or Android? Okay, and Olivia? iPhone. So iPhone 4S or better. Did anybody do it with Android? I don't. Okay. Anybody? All right. So hopefully you'll be able to do it by. So like if you're at work, if you have to work Friday afternoon from 3 until 9 or something like that, maybe you can catch a coffee break at 4 or a 3:55, and then be ready at 4 to use your iPhone to get in there and click. Now, for those of you that are in Group V for Victory, you may have noticed it on the right-hand side. This is a screen grab from one of the other students in class, Caroline. She's in V for Victory. And over here on the right side, just to the right of Professor Galileo, is the link for the V for Victory group. So what you do is you look for that V for Victory over there, and then you click, and that'll take you to the V for Victory. It's like a little mini web courses area. Okay, and there's a page in there that you'll use for sign up. So it'll look a little bit like last time. This is the page that you will see. You'll see the V for Victory photo. When you see that and the lettering in blue, you'll know that you're at the right place for sign-ups. And I'll be putting the sign-ups link right in here in this square, in this rectangular box, kind of like I did last time. And then down below it, of course, you can get in there right now. And right now you can look at everybody's schedule. All right? And so at 4 o'clock tomorrow, if you're awake, if you're not asleep, if you're not snoozing and doozing, you'll be able to go in there tomorrow at 4 and check the schedule and then click over to join. All right? And the rest of you guys, it'll be 6 p.m. Now, questions about that before I continue? Olivia. V for Victory, Olivia's asking me about V for Victory group. Those are the students who, for various reasons, I'm giving first dibs at a study group, which is partially based on exam average, on exam 1 and 2. Okay? Now, on that topic, just to let you know, I haven't finished grading exam 3. Those clicker questions, I'm still fussing with those. But when we do have those published, look in discussions, and I'll give you a little description of how to handle best 2 out of 3. Because once that's graded and up, you'll know your best 2 out of 3. And hopefully you go up from what you have in the first 2. Question in the back. Yeah, there is. You're out of luck. SOL, which is an old Latin phrase for toast. You're toast. Dude, it's just, there's never enough space. But by the same token, I make sure that there's enough people in group, that I make the first group small enough that if they all select, they all have a shot at getting in. But usually there's spaces left over, but it's not guaranteed. So if you get in there at 7:01 and they're all gone, that's it. But we have other bonus point activities going that don't rely on the finite number and the finite size of these special study groups. So you're not totally SOL. You're semi-SOL. So you're not burnt toast. You're just kind of slightly singed. Okay. Question over here. So effectively, yes, the V for Victory group would take up all the spots. And the reason for that is we didn't get as many SSG leaders as I was hoping for. A few more than I expected to turn me down. So it's always like that, and I wish we had more spots, but theoretically, yeah. But don't. That's only theoretically. In practice, usually there's more than one spot in a study group that you can nab if you're fast. If you get in there at 6:01. But by 6:05, forget about it. What? It could be by 5:30. You're right, and you won't know about it until 6:01. But it probably won't. So I recommend that you be alert and try to get in there at 6. Question over here. We didn't get an opportunity to do it last time. Shouldn't we be able to get it first pick this time? No. It's still the same. Yeah, it's still the same people that get the first shot. But if things go like they usually do, you should have at least the possibility of getting something at 6. And as I said, I'm sorry, I wish we had more spots, but okay. Let us continue. My final mention of our quote of the day, this is from Neil deGrasse Tyson. The center line of science literacy, which not many people tell you, but I feel this strongly, and I will go to my grave making this point, is how you think. Scientific literacy, which is why basically you're in this class. The powers that be felt that having a science class of this type, even if you're not a science major, will make you literate. Your science literacy will be improved. And it consists of, in my opinion, and in the opinion of Neil deGrasse Tyson, how you think. And remember, I'm always telling you, think. Read carefully and think. And on exams, if you want to crush the exam, you've got to be able to think. And many of you have made strides in that area, and I'm really proud of a lot of you that I've been able to observe this semester. All right. Now, last time we discussed the atom, the size of it, the fact that most of it's empty space, And we asked and answered the question why the atomic system is stable. In other words, why don't those electrons just kind of spiral down, losing a little bit of energy every second until they collapse right down into the nucleus? And the answer to that was written or begun by Prince Louis de Broglie of France, who said that if you want to understand why electrons have a ground state and no lower state than the ground state, and why atoms have countable orbital energy levels and not any number, a continuous infinity of energy levels, if you want to understand that, you have to think about the electron as a wave. Now, part of the reason that that was reasonable, at least to Louis de Broglie, was that everybody knew that light behaved as a particle and as a wave. Now, light, they also knew, was a massless particle. But by the time he came up with this hypothesis in the 1920s, they had already verified Einstein's theory of general relativity, which showed that even a photon with zero mass will interact with the gravitational field of the sun or any other astronomical object and curve as if it did have some mass. And it will even orbit a black hole as if it had mass, even though it does not have any mass. So it was a righteous and a reasonable proposition to think, yeah, let's try electrons with wave properties. Here's the image that I mentioned. Here it is. I snipped it out this morning for lecture, figure 8.5 in the textbook, showing that the electron waves bound to the atom, you should think of them as interfering with themselves, and in that interference effect, only at levels where there is constructive interference. So you can't have a standing wave at any elevation, above, at any altitude above the nucleus. Only at certain altitudes will the energy and momentum conditions be right, where you get one full wiggle along that circular radius, that circular orbit, or two full wiggles. Because if you don't have two full wiggles, you're going to get destructive interference. But if you have one, exactly two, exactly three, you get constructive interference. And that is how nature chooses out certain modes and only certain modes for the orbital states of the electron wave in an atom. The hydrogen atom is the one that we talked about, but we now believe that this is acceptable and worthwhile theory. It works. It fits for all atoms. And all atoms are more complicated than hydrogen. We have a fairly good theory for hydrogen. We've got it worked out to a lot of degrees. But even helium is tough, a lot tougher than hydrogen. So something like uranium atom, which is the heaviest naturally occurring atom that we've got, is pretty tough. But we're working on it for all the tougher atoms. But the basic idea is the same, constructive interference. This is how nature excludes some orbital levels. Now, in the first development of the quantum theory by Niels Bohr, he just said, okay, there's these certain levels and only these certain levels. And he didn't really say this, but he could have. I have no idea why this is so. I have no reason to expect it to be so. It does work. And he showed how the math works and all the calculus works. But de Broglie is the guy that showed why it works. And it's because of standing waves. Here's another image that we looked at last time, and we talked about constructive interference. We also compared the atom to a guitar. And I said, if you take, Sarah, a guitar and you tune it, by tightening the strings or maybe loosening them up a little bit and then go to the next string and so forth, you will only have 6 different modes, 6 different notes 6 different pitches, 6 different frequencies, 6 different wavelengths, and only those wavelengths in the fundamental mode of each string. And if you think of an atom the same way, so the atom may have several orbits, a guitar may have several strings, but once you set the strength of the interaction, and go ahead and make a note of this, when you set the strength of the Coulomb interaction, that's the force that holds the electron in orbit. Once you set that by specifying how many protons in the nucleus that are pulling electromagnetically on that electron, then you've done the same thing as setting the length of your guitar. You have a length scale for your guitar, and once you've set the Coulomb interaction strength, you've set certain energy levels for your atom. So the atom is like, as I say, a quantum guitar. It's kind of cool. And a guitar is a quantized system. There's nothing bodaciously coolness about quantization. It's just that the quantization of a guitar is like the quantization of music. Anybody that's had music theory knows that musical notes and the scales and stuff, there's all kinds of math behind and geometry behind that. Okay, so there's nothing bodaciously amazing about that. But what happens is, if you assume that matter has waves, it has amazing implications. Now, here's a simplified picture of a hydrogen atom. And we talked about n equals 3 to n equals 2 transition for the H alpha photon, the red photon. These formulas, lambda equals h over mv, lambda equals h over p, those are the de Broglie relations that relate wavelength and momentum for every system. And so make a note, every dynamical system that has momentum obeys this relation. But not every physical system, not every dynamical system exhibits quantum effects. Right? The quantum effects, like diffraction of electrons, which I'll show you a picture of, it depends on the wavelength. And this is the equation that controls the wavelength. I told you last time that there's a combination of words I like to use. We think of, in Newtonian physics, we think of a baseball as an example of a particle, and we think of a wave in the ocean as an example of a wave. But we don't think of any objects that have, in the Newtonian physics world, the world of Sir Isaac Newton, that have any of those properties in common. But in the quantum world, we found that, yes, they do. The electrons are so small that they have wave properties as well as particle properties, and at the same time, full time, 24/7. And so the two words that I put together to show the amazingness of that is that an electron, or any quantum particle, any particle from the quantum world, is like a bookcase that is also a horse. I just saw somebody in the middle row go, "What? What is Dr. B talking about?" Think about it. A bookcase. See, that's exactly my point. What does a bookcase have to do? How can a bookcase also be a horse? Well, in our everyday world, we would never think that. But look at this equation here. Wavelength. And then over here, MV. That's a baseball has MV momentum. All right? So, okay. So the same guy that said, "What? It's going like this?" Okay. It's a little less dubious now. But it really is true. It is a shocking thing, and physicists have scientists around the world in the day of de Broglie and to this day have a hard time swallowing it as well. But it really is as weird as saying, I have a bookcase that is also a horse. It is that weird. An electron that has particle properties and wave properties at the same time, 24/7, never one and then the other, always two, both at the same time, it's hard to swallow, even for a scientist of this our day. So, join the club. Anyway, it's for that reason, and this is where we left off last time, after everybody stampeded out of here. Okay, technically I was out of time, but anyways. For the reason that we just saw, those two equations, the de Broglie relation, H was the thing that's in, that is the constant, it's a constant of nature that is kind of the connector in the equation between particle momentum concept and wavelength wave concept. And for that reason, I like to say that Planck's constant, it's more important than Newton's gravitational constant. Coulomb's electromagnetic constant, the Coulomb constant, it's more important than G. It is the one constant that every dynamical system must be in relation to. Every dynamical system has quantum properties and obeys the de Broglie relations. Planck's constant is the one constant to rule them all because of the de Broglie relations. Because every particle, now, every particle has wave properties. Now, you might not appear to have wave properties. In other words, when you go through that door in the back of the room, you don't diffract. When you start down here at the bottom and you head towards one on the door, you don't diffract through both doors. But electrons do that. Obviously, electrons do that. Measurably, they do that. Observably, they do that. Now, we can't do it, but theoretically, we are waves. When you're walking up there, you have momentum. Therefore, you have a de Broglie wavelength. And your homework tonight, yes, I said homework. Your homework tonight will ask you to calculate some de Broglie wavelengths, some simple ones. I'll try to make them simple. And that is why you don't see diffraction through the door. So let's go and ask this question. How is it that Planck's constant rules them all? What are you talking about, Dr. B? Planck's constant. How dare you? You know, well, it's not me that dares. It's the good Lord himself. You know, H rules all of matter everywhere. Every dynamical system that has energy and momentum, all right, so that's everything, obeys the de Broglie relation in some way. But where do you look? Where do you find it? You know, how do you see signs of this constant that, you know, and this whole concept of matter behaving as a wave? Where do you get that? All right, light waves, yeah, we could see light waves diffracting through diffraction grating, except in this classroom you can't because you can't turn the lights off. But there's the first place where you look, diffraction concepts. And we've talked about diffraction earlier this semester, how it depends on the wavelength of the waves going into the aperture. You know, in other words, the size of the gap, whether it's a jetty out in the ocean or it's the gap size in a diffraction grating or any other diffracting system, those two distance scales, aperture and wavelength, they have to be in the right ratio in order for you to get diffraction. And then the other place where you would see a lot of Planck's constant ruling them all is the periodic table, Chapter 9. It's a Chapter 9 concept. Before we get to periodic table, though, I want to talk a little bit more about diffraction. All right, now, if you recall from Lecture 22, we looked at this image, and we talked about the fact that, okay, depending on the wavelength of the wave going through the gap, let me get my... I wish I could see that. There we go. Okay, here's the gap where my cursor is. All right? And right below that are the waves coming in. Those flat lines, bright and dark, those are the waves going into the barrier. And they go through the gap, and that's where the wavelets appear to form, and then you get diffraction effects. Now, you get a little bit of diffraction here, but not much. And it depends on the ratio of wavelength and the gap size. All right? And for that reason, it's possible to have a wavelength that is too small for your aperture. Write that sentence down again. It is possible to have a wavelength that is too small for your aperture to produce noticeable diffraction. It is possible to have a wavelength that is too small for your aperture to produce noticeable diffraction. All right? Now, what that means is, if your wavelength is a little bit bigger than that, you might see some diffraction effects. You might see diffraction energy, kind of bending off to the left and right. And this one's got a little bit. It's faint. But we looked at other diffraction images that showed quite a bit of diffraction. Now, how does that relate to the de Broglie relation? Well, here it is. If you have too much momentum, you've got a big denominator. H doesn't change. Planck's constant, that's a constant. Okay? And so if your momentum is too big, that means relative to Planck's constant, you're going to have a really small wavelength. And that's why every single human being in this classroom, and if there's any space aliens from another planet, everybody in this classroom has momentum. As soon as you move, you have too much momentum to get very much of a wavelength. Your wavelength is too small. So write that down. Human scale, wavelength is too small because momentum is too big for Planck's constant. So Planck's constant kind of puts the kibosh on your diffraction effects. One constant to rule them all. Sorry, too much momentum. And that is why when you as a human being, when you walk through that door or you even head for that door, you're not going to diffract. It's not going to be noticeable. A little blood cell going through your veins and your arteries, pretty small. I don't know if you can see it. Well, you can see it with a microscope. So a microscopic particle, even a blood cell, too much momentum. You'll not see blood cells diffract through an artery, through where two arteries diverge, for instance. You won't see that. They'll go through like a particle. Electrons? Yeah, every day. Molecules? Yeah, baby, every day. Every day, all day. They'll diffract until the cows come home. If you're an electron or a proton, your momentum is tiny because you're tiny. The mass of an electron is like 10 to the minus 27 kilograms. Whoa. That's really small. And you're like, a few dozen kilograms. Okay? Maybe 100 kilograms or so. And an electron, 10 to the minus 27 of a single kilogram. So forget about it. They got really tiny momentum. And so what that means, Stephen, is that you have a small denominator. Small denominator, big fraction. And so you get diffraction patterns like this. This is what you would see if you shine a beam of electrons through a crystal of magnesium silicide, Mg2Si, crystal. Everyday crystal, magnesium and silicon. And if you beam, like an electron microscope, if you beam the right kind of electron microscope through a crystal, you'll see this pattern. Now the central, this really, all right, where I have my cursor, that's the central image. All those little dots around it in a hexagonal pattern, those are diffraction patterns made by electrons. And when Davison and Germer observed electron diffraction back in the 1920s, they verified what de Broglie had suggested. His theory was righteous. As soon as they saw stuff like this, they said, yep, ding, electrons really do behave like waves. Question? Does Planck's constant have a rational value that we can kind of sort of know? The answer to that is yes. 6.67, I think it is, times 10, no, that's Newton's constant. 3.31 times 10 to the minus 34 joule seconds, I think. It's in your textbook, look it up. I don't have it memorized. I almost have it memorized. But it's a pretty small constant. So to get a wavelength and to have a momentum that's not too big for Planck's constant, you've got to have a small object. And that is why only electrons, protons, neutrons, molecules are small enough to have significant quantum effects like this. If you had a wavelength, a de Broglie wavelength of a few centimeters or a half a meter or something like that, this is what you'd look like going through the door. You'd diffract off into all the, you'd have a lot of diffraction up and down and a lot of diffraction left and right. Be kind of cool to look at you walking through a door. Wow, that'd be kind of cool. Talk about a Hollywood entrance, baby. That would look cool. But unfortunately, you do not have a de Broglie wavelength that'll produce this. You're just going to get, all you're going to get is this. You're just going to get the unperturbed image. You're not going to get any dispersion. Now, let's talk about periodic table of elements. The person who developed it was Professor Mendeleev, which hopefully you read about in the for the homework assignments. He originally based his idea of a periodic table of elements on the properties of the various elements that were known in his day. Now, we've since discovered a lot more elements and refined them from rare species of rock and, out in space and stuff like that. But if you correlate the atomic weights, in other words, if you take the same amount of hydrogen and call that 1, then the same amount of carbon is going to be about 12 times as many grams as what you've got for hydrogen. So if you got 1 unit of hydrogen and the same number of carbon atoms, the carbon atom is going to have 12 times as many grams. And that's its atomic weight. They knew that. They didn't know anything about electrons and stuff. But he said that if you stack things up by atomic weight and kind of shift your columns and rows just right, then you'll get, on each row, you'll get the similar properties. So on this, for instance, on this one, we're going to look at this row up here. I can't really put my cursor on it, but on this, in this diagram here, on the right side of the screen, you can see copper, silver, and gold. 3 beautiful metals, 3 really good conductors. And those are physical properties of those atoms, those elements. And Mendeleev said, "Whoa! If you organize them by weight, relative to hydrogen, they all seem to, you seem to get stacks. Everything stacks out into common properties." But he didn't know anything about atomic components, protons, neutrons, and electrons. What are atomic weights? Well, an atomic weight is basically the sum of the number of kilograms in all your neutrons, the number of kilograms in all your protons in the nucleus, and the number of kilograms in orbit in the electrons. All right, now the electrons don't really contribute much. We can measure the contribution, but a proton is about 2,000 times the mass of an electron. All right, and a neutron is about the same size. So a few protons or one proton is going to mass 100 electrons. gram for gram. But we can still measure it. Okay? So the modern periodic table goes by atomic number. And here's what the modern periodic table looks like. This one is stacked. So Mendeleev's periodic table was organized by row. Modern periodic table is organized in stacks or periods. Here's period 1 and period 2, group 1A, group 2A. The alkali metals, everything in that first column except for hydrogen. So lithium, sodium, those are called alkali metals. They'll have similar properties. They're easy to oxidize. It's easy to steal their outermost electron. Beryllium, magnesium, those are called alkaline earth metals, and they both have similar properties. They're very light, but they're metal, and they're very light, kind of brittle. And all those properties Mendeleev found, he found it sideways. Modern day, we have it stacked up this way in racks. And but this is basically what he did. And there's another couple things that I want to show you, modern day versus Mendeleev's initial thing. Take a look at, I can't get my cursor on it, but if you look about 2/3 of the way, 60% of the way across, you'll see the copper, silver, and gold. Copper Cu, gold Ag, copper Cu, silver Ag, and gold Au. They're stacked together. Here's a close-up. Go ahead and jot those numbers down. Copper's atomic number is 29. Its atomic weight, 63.546. Silver, its atomic number is 47. Its chemical symbol is Ag, and its atomic weight is 107.87. So what that tells you is that the nucleus of a silver atom is 108 either protons or neutrons. Now, what the atomic number, 47, tells you is, in the nucleus, 47 of those 108 are protons. So the atomic number tells you the number of protons in the nucleus. The atomic weight tells you the total number of objects. So that's protons and neutrons. So if you subtract the two, as you will do on clicker in just a few minutes, yep, clickers, better get them out. One more clicker question to train your brain. So here's Mendeleev's table. And notice he didn't have a whole lot of elements in there. He had a good number, but the other thing that he had was gaps. If you look at this, there's a couple gaps that are visible, and Mendeleev said, this thing looks good, it looks periodic to me, and therefore I predict that in those gaps, somebody in Sweden or Norway or somewhere, or maybe South America or South Africa, is going to discover a rock with that element in it. And they were right, or he was right. They were able to find it. Now here's the alkali metals, lithium and sodium, and then over here these guys are copper, silver, and gold, and we got kind of a gap over there next to the. And here it is again. Here's a close up. Here's copper and silver, and you can see that he had it pretty good, 63.4. We're a little bit different from that now, but you know, it's still the right ballpark. And silver, 108, that was good. And then Au, he's got a gap over here. Right, I think it's right here. I can't really see the cursor, but yeah, Au is right over there. All right, so his thing was horizontal. He was going by atomic weight. What we do is we go by atomic number. So let's and go ahead and make a note of this website, webelements.com. Really nice periodic table. This is the web address for the the blurb page on gold. I shouldn't call it a blurb because it's like an encyclopedia about gold. Every element that you want to think about in the periodic table, just look at it and click on it, and you'll see like its melting point, all of its nuclear properties, its abundance in the Earth's crust, everything. It's a really nice website. I use it a lot. Anyway, so here's copper 29, 63.55. So that's a little bit different from what Mendeleev had, but still pretty close to what he had. Or he was pretty close to this. Silver 108 is pretty good. Gold 197. So let's focus in on this rectangle, this tile of the periodic table for gold. All right, the name and the chemical symbol, of course, in the periodic table. Usually in this structure. Down at the bottom, the atomic weight. And basically that atomic weight is relative to hydrogen being 1 and carbon being 12. It's actually based on carbon being exactly 12. That's the atomic mass unit. Carbon is declared to be exactly 12. And then if that's true, then gold is 196.97. Pretty close to 197. And therefore, it tells you that in the gold nucleus, a regular gold nucleus that hasn't been in a nuclear reactor for a week or anything like that, a regular gold nucleus that you dig up out of the earth is going to have 197 either neutrons or protons. And then this number up on top, 79, that tells you how many protons. So by doing a subtraction, you could figure out, using the atomic number and the atomic weight, you can figure out how many neutrons a typical gold atom or any other typical atom of any other element has. And final comment about this particular tile, the atomic number is where the periodicity really is. We saw Mendeleev's kind of wobbly looking periodic table. It was good enough for the day. It was good enough to say, yep, we definitely have a pattern. But the real thing that got it locked in, a stone cold lock, was not atomic weight, but the atomic number. If you do everything by atomic number, it really racks and stacks right on the money. So let me ask you a clicker question here, based on this tile for silver, for gold. How many neutrons in a typical gold nucleus, please? Fifteen seconds. What happened? Did you click? Okay. 5, 4, 3, 2, 1, 0. Oh, you guys aren't the genius section today. You got 89% correct. But the morning class had 92%. Anyways, you're still pretty good. For those of you that voted for 79, no, 79 is the number of protons. So if you voted for 79, make a note. 79 is a true answer if I'm asking for how many protons. But if I'm asking neutrons, take 197, subtract 79, and that's the leftovers of the nucleus. Those are the neutrons. And the periodic table can help you figure that out for any atom, not just gold. questions before we continue? Yeah. Yeah, usually, yeah. The reason that sometimes a number is not really close to a whole number, like this was pretty close, but copper wasn't. And the reason for that is there's different, in nature, there's some copper that has 63 nucleons. A nucleon, Nucleon, is the generic term for anything in the nucleus, so proton and neutron. The atomic weight tells you the number of nucleons. So some copper has 63, some has 64. And we can analyze copper and break it down into they're called isotopes. The same chemical properties, slightly different nucleus, one extra neutron. And so some elements are like that. You know, like carbon. Well, carbon is mostly carbon-12, but there's carbon-13 and carbon-14. But on a test, I'll be giving you if I give you a problem like this on the test, it'll be with a number that's clearly, either rounded up to 197 or rounded down from, 122.01 to 122. Okay, so I won't do anything dubious or difficult. All right. So in the periodic table, I said that this is the area where one constant rules them all. And it's the de Broglie relation again, and it's those electrons. Almost all of the chemical properties of an element, all the chemical properties of a molecule have to do with the electrons. And the electrons obey the de Broglie relation. When you get into a molecule, it gets a little bit tough to do. You got to do a ton of calculus. Enough calculus to choke a mule, but you could do it. But the interaction controls the orbits, and H controls them all. One way to say it is, okay, you can have any orbit you want, but you've got to divide yourself into me. Your orbital momentum has to divide into my fraction, and I'm on the top of the fraction, so I call the score. I call the music. I call the tune. Okay? Your puny orbital momentum and energy must be divided into me. Right? Not the other way around. Because Planck's constant holds for anything, whether it's your left earlobe or an electron. Planck's constant applies to all of them. But it has different verdicts. For an electron, yep. For your left earlobe, not really. Quantum effect-wise, anyways. Now, these orbital sizes, shapes, and energies control how atoms combine. And we saw that when we looked at the water molecule. It had a very precise angle formed by the hydrogen, the oxygen, and then the other hydrogen. I think it was like 104.4 degrees, the dihedral angle of the water molecule. That is controlled by the orbits. And the orbits are controlled by Planck's constant. Molecules also have orbitals, and they are chemical compositions or chemical compounds that are formed when one atom binds or bonds to another atom. Like H2O, that's an oxygen bound with two hydrogens, the water of life. It's kind of interesting, water, H2O. Hydrogen is like this explosive gas. If you fill up, like the Hindenburg disaster, it was a dirigible, a big airship that was filled with hydrogen. It was nice, lighter than air, very good for a dirigible, an airship, but it got a spark and it detonated. It killed all those people. So hydrogen, yeah, very hostile. Oxygen, corrosive. And it's the thing that you can't have a fire without oxygen. But together, hydrogen, explosive. Oxygen, combustion fuel. Together, H2O, the water of life. Isn't that cool? And they're a molecule controlled by Planck's constant, the one constant that rules them all. Now, other molecules They have things called covalent bonds, in which an atom will share an atom and thereby bond together. They'll be tighter together. They'll rotate around with each other, okay, by sharing an electron. And that's cool, a covalent bond. Good example of that, carbon dioxide. It's a carbon and then two oxygens, left and right. And they share an electron. Actually, they share two electrons from each oxygen. An ionic bond. Now, here's another one, sodium and chlorine. Whoa! Chlorine, that stuff it'll kill you. In World War I, they used chlorine as a weapon of mass destruction. The sodium is extremely dangerous too. Sodium, if you expose sodium to air, it'll interact with the water vapor in the air and explode. And that happened in my high school. When I was in high school, the chemistry department chair was messing around with some. Well, he's trying to handle some sodium, and he slipped or something. It blew up the lab. It blew. They had to evacuate the school and everything. It was kind of cool, actually. We got let out half a day of school that day. But he was all right, but it was still pretty. But it's sodium, it'll blow up. It's explosive. But yet, when the chlorine ionizes the sodium, which it can easily do, they bond together and form NaCl, salt, the salt of the earth. And that's one of the cool things about compounds. They might be poisonous or dangerous on their own, but in a compound, totally different, because the orbitals are different once they've bonded together. Polar covalent bond, that's another kind of a bond, not perfectly balanced. Okay, and that gives water its distinctive dihedral angle. Now, carbon dioxide doesn't have that, but water does, because it has a polar covalent bond. So sharing electrons, but not perfectly symmetrically, atom to atom. Carbon dioxide, it's more of a symmetric sharing. So the periodic table shows you at a glance how all these things interact, and we call it chemical bonding. So let's go back to our analogy, the quantum guitar. Okay, an atom is like a quantum guitar. You set the interaction strength, and then there's only one way to tune it. Only one set of orbits allowed, and they're numbered. It's very specific energy, very specific orbits, very specific colors of light emitted, very specific bonding. If that is the case, that a single atom is like a quantum guitar, then this would have to be called Mendeleev's orchestra, baby. Because that's all the atoms, all the different atoms. And so think of them as all different kinds of instruments in one big orchestra. And what do orchestras do? Well, they go around wearing tuxedos and stuff, but sometimes you have a soloist. You go to a concert. Here's a soloist. Carbon. That beautiful diamond, that's carbon. That's one kind of atom from Mendeleev's orchestra. Water. That's not a soloist, that would be a trio. Pungent ammonia. So write down NH3, ammonia. 1 nitrogen, 3 hydrogens. In Mendeleev's orchestra, that's one of the many quartets that you can make. So they perform it as an orchestra in general, but most of the time they're off operating as quartets. And here's the big band. There's a lot of players in this one. A lot of instruments, and they're all playing together. DNA. the beautiful double helix structure of DNA, the genetic code. Isn't that nice? Water. So when you're drinking a glass of water, it's like drinking a song. It's like drinking music. Isn't that cool? It's nice. How about this? A magnificent wave in the ocean. Whoa. That would be an exhilarating song. All those H2Os. And there's salt. There's Na. There's Cl in there. And there's energy in the atmosphere, the wind taking the top off that wave. And then, of course, the best symphony of all, us. That is the best. And so, my wonderful students, this is my last physics slide of the semester, and I want you to remember it. Now, before we dismiss, I want to spend a few minutes I want to spend a few minutes with these talking about getting ready for the final. This is a selfie for one of our SSGs. I love getting those selfies. All right, so let's. You're not dismissed. If you want to come to the final, you better listen up. Final exam for us, December 10th, right? That is a week from today. We start at 10 a.m. So don't come in at noon, or you will not be able to take the test. The morning section, they have a different date. But for us guys in this noon section, Thursday the 10th, 10 a.m., be there at 10 a.m. sharp. Now, it's 3 hours basically. But the test is twice as big as a midterm. So roughly 2 hours of work, 3 hours of time. It shouldn't be a rush to finish it. So, but I mean, you still want to work as quickly as you can and finish it, but you don't want to feel rushed, but you still want to be on time. All right, here's what to bring. Oh, by the way, homework tonight, we'll have a little bit of regular homework on periodic table and stuff, and the Mendeleev's orchestra. We'll also have a big mega review. Wait a minute, let me back up. The regular homework on Mendeleev's orchestra, the periodic table, that'll be due Monday, and we won't have a Tuesday class next week. Tuesday is study day. So it'll be due Monday at midnight, so just get it done over the weekend. And then there'll also be another assignment, a mega review that's not going into your homework grade, but it'll be a big, 25, 30 question homework assignment from the first concepts of the semester all the way till today. And that'll help you get review. You can use it as a study tool. I'll put some brain burner calculations in there. And what I will do with that, for the students that you couldn't get into SSG, you'll be able to get some bonus points out of that. So I'm going to go, so if I have like 25 points, I'll scale your performance down to, something out of 3. So you might get 3 bonus points out of that. Also, the bonus point discussion area is 2 bonus points, but only if I select your question for the final, and you won't know that until December 15th. So, but it's a good study tool, and go for it. Question? How many clickers on the final? Good question. Just think of a regular test and multiply by 2. So maybe 10 clicker questions and about 90 dots. You'll be seeing dots on both sides of the Scantron. And so let's talk about that now. For the test, number 1, bring your ID. Number 2, always bring your ID to the final. Okay? I may check IDs. Number 2, bring your Scantron, of course. Pencil, a good eraser. You know, one of those pink rectangles from 3rd grade type situation? Calculator. You may not use your cell phone for any reason. All right? You may not use it for a calculator. You may not use it to communicate with anybody for any reason. And if we do, you'll be punished for it severely. If you do, we'll be punished severely. All right? So just get a regular calculator and study, and you'll avoid that. I don't want to see any more of that. Ever. Bring your clicker, and make sure you got some good batteries in there, and don't forget it. All right? I'm just trying to think. So you'll probably be done by lunchtime. Be ready. And last thing I want to say, and this is something good. There's hardly a person in here that I can't look at and think, yeah, it was really fun having. And just even though if I never knew your name, if I never called on you, I still look at you. I'm always looking at you guys. And I'm up here blabbing my mouth, but I'm looking at you guys, and I look at you guys working when you're doing clicker questions and stuff. I love seeing. It's been a lot of fun, and I really have loved having you guys. Yes, even you, Serrano. It's been a lot of fun, and I really enjoyed it, and I want you to know that for real. Okay? You're dismissed. I'll see you at the final. If you want to get your exam printouts, come on up. And Corey, come on up. You can ask your question. Do you need printouts? Derek, can you do printouts? And I'll do regular questions over here, and I'll get this stuff done.